Alright, so now we're going to cover stacks and queues in C++ and go over their big O. So here is the documentation for the stack in C++. And one of the things you'll notice is it's, first of all, a stack is just a last in, first out container. And it is implemented as an adapter, a container adapter. And all that means is that, there's a lot of other containers that are really similar to stacks. Queues, vectors, and stacks are all have a lot of similarities, and so instead of having separate implementations, they all share the same implementation, and then they have whatever variation that they need. They're kind of encapsulated in that way. So another thing I wanted to talk about is just some of the functions. So we talked about last time how stacks, they have the last in, first out nature to them, and you push stuff on top, you pop stuff off, and then you also have top, which just is able to view or get a copy of whatever is on the top, or not get a copy of, but is able to access the top element of the stack. So you can see that pop does not give you anything back, it just removes it from the stack. So top is the only way to actually access that top element if you need to change it or use it for something. And there's other member functions associated with it as well. If you've never heard of the term API, it stands for Application Programming Interface, I believe. Just Googling it to make sure. Application Programming Interface, and it's another one of those terms, it's used a lot. It kind of means the same thing as a library or the standard C++ implementation, or using another class that you didn't write. They're all kind of the same thing. They're libraries of functionality that you're using. And so the Stack API, what that means is what is the language that you can use to use on a stack object in C++. So we're going to go through the same things I did with the vector. It's the constructor, implementation, and then go through that example where we see insert, access, and search, and then summarize its big O. I'm going to do this fully with the stack, and then I'm not going to go through all of it with the queue because it's kind of repetitive, but I'll show any differences in the two. So the constructor is really nice. It uses the stack as the type, and then you put in the brackets whatever type of elements you're going to have in your stack. And again, lots of different constructors in C++, so this is just one of them. Remember that the constructor is what actually allocates the memory for your data, and it's what creates the object. And that object is going to be the object of whatever class you're calling on. So in this case, it would be the stack. Here is a little bit more about the implementation. It shows up in the documentation, and you can find this for all of these containers. So, like I said, it's a container adapter. So as long as these operations are supported in a container, it can adapt. The stack can be adapted off of lots of different containers. So it could be a vector, a deck, or a list under the hood. So the default is that the deck is used as you can kind of just think of it as the data structure behind the implementation. And remember, a deck, we talked about it a couple weeks ago, is a double-ended queue. So it's just a linked structure that's able to keep track of the data. And that makes sense for a stack, right? Because you just have to keep track of order and everything has to be connected. So that is a little bit about the stack implementation. We are going to go into the stack implementation as one of our first implementations that we go through in a couple weeks. So again, same problem as before, just reading in some UINs and some net IDs, and then going through and filling up some stacks with that data, printing out some data, and then searching. The thing to keep in mind about the stack is that you shouldn't really be doing any of these things with a stack. So I wanted to show you the same example with a stack, but there's going to be lots of warnings, do not do this, do not do this, because this isn't what you would use a stack for. This isn't a good use of a stack. You shouldn't ever search a stack, basically, and I'll show you why in a second. So first, filling a stack, no problem. There's really nothing tricky about it. You just use the push function to put stuff into it, and then it just puts everything up into the data structure. The rest of the code here is the same as the vector code. It's just the file reading code, and this is the only code that is special to a stack. So we're just putting in some pass by reference stacks in here and filling them. So what's the big O of insert? Stack has big O of 1. And it's one of the advantages of a stack is that you can only push something to the top of it, so it's always big O of 1. With the vector, insert depends on where you insert, and stack takes that possibility away from the user because the programmer no longer gets to decide where to insert. It's only allowed it to be inserted in the one location. Access is here. So this is the tricky part. So in order to access something in a stack, you need to call top. And top is actually what returns the element and gives you access to the element. And then the tricky part is if you want to print out the stack, you no longer can use a for each loop. So for each loop doesn't exist in a stack. There's no such thing. And that's because it's not iterative. You can't like iterate through it because you only have access to the top, right? So it kind of like would break its behavior if you were allowed to iterate through it. So the only way to walk through a stack is to basically empty it. So you set up a while loop until it's empty, and you basically return the element from top and then pop it off. So remember, top just shows you the element, and then pop actually takes it off the stack. So when you run this, it does print the stack just like it printed the vector, and it looks the same. But the key is that at the bottom, your stack is empty, right? Because that's what this condition says, keep iterating until it's empty. So it's not really a type of data structure you want to use if you need to constantly keep going through your data and walking through it. It's just not what it's for. It's for when you need to put something and take it out in a certain order, but just like not all at once, like not look through it. So like if you need to reverse the order of something or yeah, that kind of thing. So that's how access works. Again, big O is 1 because you can only do top, which just looks at the element, so that's O1, right? Like you're just grabbing an element that's available to you, and there's only one of them, and the implementation keeps track of that. And then pop is the same thing. You have access to that in memory as well, so you can remove it from memory. Let's look at search. Oh, and then the other thing I wanted to point out is that with a stack, you do not want to pass by reference because when you're printing it out, it's clearing it, right? So if you want to print out a stack, you want to make sure you write a function, call the function, and then make sure it's not passed by reference. It is not efficient to do this because it's making a copy and then it's like destroying the whole thing inside the function. But if you need it for debugging purposes, or if it is appropriate to do for whatever reason on what you're doing, you would want to make sure that you do not pass in your stack by reference for printing or walking through it. So same with search. So if we want to search a stack, we're going to do the same thing that we did before. So here is the code for search, and it's the same idea as the vector, where you're basically going to walk through the vector and compare every element. So here we're comparing every element. But what's different is that the stack is emptying as we're comparing it. So our stack is going to be left with whatever's left over from what we found. So let me show you this in code. Keep those for now. Where's my dog? He is making that noise. Okay, so here's the code. So I'm filling it, I'm printing each stack, and then I'm searching it. Okay, we're going to just need to take a little pause. Alright, so we have 2 stacks. We're filling them from file, we're printing them, and then we're searching them, and then printing them again after we search. So depending on where we search, so if we go to the search stack function, this is the same function I just showed you on the slide. Depending on where we what we search for, at the end we should no longer have anything left in the stack, or only have partial of the stack left over. So let's see what it looks like when we run it. Okay, so these are our 2 stacks printing out. Then why don't I search for the last one? Or no, I'll search for the there'll be 2 left at the end. So I'm going to search for this one. So here, searched for it. So it says it found it. But now what? And it printed it out. So now I'm going to end it. And it prints again at the end. And here it's left because I didn't pass it by reference. But it did find it. So now let's actually pass it by reference, and that way we can see that it will erase it. So here I'm going to go up to the stack and do both the prototype and the original by reference. We'll do the same thing. Really slow. Come on, you can do it. Okay. Okay, so now I'm going to do this one again. I'm going to copy that one and search for it. Okay, so it found it. I'm going to stop. And you can see that my stack only has those 2 left over because we destructed everything else. So that is a little bit about how stacks work and how they're different from vectors. Okay. So the big O of a stack search is O of n, but really it's kind of like, it's not what it's for. So you shouldn't be searching stacks, and that's why I put a bunch of notes in the comments. And you shouldn't be printing stacks really, unless you're just like looking at them to debug, because it's just like not the nature of them. Because they, you have to destruct them in order to do these things. I mean, you can print them. I'm not trying to say you can't, but if you can avoid it, it's good, because it's very expensive, because you have to make that copy in order to print it. So just like a vector, the search is O of n, because you have to go through every element in order to find that element. Okay. Now moving on to the queue. The queue is very similar except for its first in, first out nature. It's also an adaptive container, and then the reference page is here. Typical operations of a queue include push and pop, which behave very similarly, but instead of calling it top, it's called front, just because of the abstraction that we're using as a queue instead of a stack. Otherwise, it would be very similar. It has the same thing because pop and front are basically equivalent. It just would do the same thing. It would just print in a different order, and you would search it in a different order. So for stacks and queues, you have O1 insert, access, and remove capabilities, which is what's great about it. So it makes it's really, really useful in lots of algorithms to use stacks and queues in different little pieces. So they are used all the time, but they're only used when you specifically need them for what they're good at, which is like a stack is able to kind of reverse the order of something if you only need, that thing, access to that very next thing. And then the queue is good for like when you need something in the order that it was received, basically. Neither of them have for each loops. You have to loop until empty. You do not have direct access to any elements, so there's no random access. So anytime you need that, these are not going to work. Searching just doesn't make sense. And again, size is the same. If you need to calculate these things like size or empty or other these member functions and you're curious, well, like what does that cost? Again, the implementation is like keeping track of this. You can basically think of it as like there's a private member variable in the class that keeps track of size, and so when you call size, it's just automatic. It just knows the size because every time you've pushed or popped, it has incremented or decremented a counter. And that's it for stacks and queues.